In this lesson, we're going to talk about rotational kinematics. This is an introduction to rotational motion, where we have, instead of objects that are moving in a straight line, they're actually just rotating or moving in a circular path. And so the first thing we're going to talk about is there's a lot of similarities between linear motion and rotational motion, or translational motion and rotational motion. Translational is a fancy word for linear. So the first thing we're going to look at is theta. Theta represents an angular position. And theta is measured in radians, and so we need to understand what a radian is. So if I take a circle, okay, and I have a reference position here, and I have a position here, it has traveled through, rotated through an angular position theta, and as it does so, this, of course, is the radius, as is this piece up here, the radius. And then it covers this distance here is called the arc length. It's a linear distance, and we'll go ahead and just use the symbol L for arc length there. Well, in radians, theta is equal to the arc length divided by the radius. That's what it is. Arc length divided by radius, that's the angular position theta. Now, if the arc length is equal to the radius, then we have theta equals 1. So theta equals 1 radian when the arc length is equal to the radius. So let's take a look at this, for example. If I go all the way around the circle, I know that the arc length is going to be the circumference, right? So the circumference is 2 pi times r. So if I look at the angle that's involved in one complete spin around the circle there, it's going to be arc length over radius, which is going to be the arc length for the whole circumference there is 2 pi r over the radius r, and I can see that theta is equal to 2 pi. So 2 pi radians is the same as what we measure in degrees. One complete trip around the circle is 360 degrees. This allows me to have a conversion factor if I need to convert between radians and degrees. I can simplify this and say pi radians is equal to 180 degrees. Now, interesting thing about radians. Radian is a dimensionless unit. Now, what does that mean? For example, look at how we find the radian. Theta is an arc length divided by a radius. That arc length has dimensions of length, and radius has dimensions of length, and so the dimensions actually cancel out, and there is no dimension to the radian. So we just call it a radian so that we know what we're talking about, but it does not have any dimensions, not length, mass, or time, any of those things. So pi radians equals 180 degrees. If, for example, I want to say 45 degrees equals how many radians? Remember, when I do a unit conversion, I start with what I'm given 45 degrees. I want to multiply by a fraction equal to 1, where the top and bottom have the same value but different units. To get rid of degrees, I'm going to put degrees on the bottom, and I want to go from degrees to radians, so I put radians on top. And that's where I fill in my conversion factor then. Pi radians is the same as 180 degrees. And so I take 45 times pi divided by 180, and I get pi over 4 radians. Now, in a math class, they would leave it as pi over 4. In physics, we typically will round to 3 significant figures. So if I take pi divided by 4, I get 0.785 radians. So 45 degrees would be the same thing as 0.785 radians. So remember, we had found that theta is equal to arc length over radius, or we could think of arc length as being a linear distance. So I could call this a linear distance, let's just say d over r. Okay, we usually use L for arc length, but we could use d. In other words, d is equal to r times theta. Now, what happens when I divide by time? So if I have theta over time equals d over r over time, for example, then theta over time, how much theta is changing in time, we call that the angular velocity. And the symbol we use for angular velocity is an omega. Looks kind of like a W, but it's actually an omega. A W would look like this. W would have pointy tips here. Omega is not a W, it's got rounded. And so it's a Greek letter omega. It's a lowercase, and that is a symbol we use for angular velocity. Now notice that what I have here is d over r over time, and when I divide by time, that's the same as multiply by the reciprocal. So what I have is d over t times 1 over r, and d over t is velocity. And velocity times 1 over r is just v over r. And so my angular velocity omega, turns out, is equal to v over r. Now, you can do the same thing with calculus. You just take the time derivative rather than dividing by time. You get the same relationship, that omega is equal to v over r. Or in other words, linear velocity is equal to r omega. Again, these are the same equation. Notice the relationship here to these equations. Now, if I take the time derivative of angular velocity, or if I divide it by time, again I have v over r over time. Now, the change of angular velocity in time is going to give me the angular acceleration. Angular acceleration, the symbol we use is the Greek letter alpha. And so again, following the same kind of reasoning here, I have v over r times 1 over t, or again, you could do this with time derivative as well, which is v over t times 1 over r, which is in fact a times 1 over r, or a over r. So the angular acceleration is equal to a over r. And again, similarly, the linear acceleration is equal to r alpha. So these are some important relationships to see between the translational kinematic variables and the rotational kinematic variables. So I've got linear distance equals r theta, linear velocity equals r omega, and linear acceleration equals r alpha. So these are some very important relationships. Now we can take those relationships and we can look at how the kinematics equations work. So kinematics equations we have for constant velocity, if you'll recall, we had d equals vt. Well, in rotational motion, that looks like d becomes theta and v becomes omega. So this is, instead of constant linear velocity, this is constant angular velocity. Then I have this equation. All of our equations, it's really nice because all of our equations for rotation, we simply take the linear equations and we simply put in the appropriate rotational variables. So instead of a linear displacement, we use an angular displacement. In place of a linear velocity, we use an angular velocity. So I can look at other kinematics equations as well. V equals v naught plus at, for example. This becomes, in rotation, omega equals omega naught plus alpha times t. D equals v plus v naught over 2 times t becomes theta equals omega plus omega naught over 2 times t. D equals v naught t plus 1/2 at squared becomes theta equals omega naught t plus 1/2 alpha t squared. Again, just in place of d, I'm putting theta. In place of v, I'm putting omega. In place of a, I'm putting alpha. I get all of the equations, they work the same. And our final kinematics equation, v squared equals v naught squared plus 2ad becomes omega squared equals omega naught squared plus 2 alpha theta. So whereas each of these equations, this is, I like to call this the don't need d equation. This is the don't need a equation. This one is the don't need v, and this one is the don't need t. Similarly, same thing with the rotation. So instead of don't need linear displacement, this one I don't need angular displacement, don't need theta, don't need alpha, don't need omega, and this one is still don't need time. Time, there is no rotational counterpart to time. Time is time, whether you're rotating or whether you are moving in a line. So that's how you can see the relationships here of these kinematics equations. And again, just a quick review, very important, that theta equals distance over, I'm going to use L over R, distance over radius, omega equals velocity over radius, alpha equals acceleration over radius. And the counterparts there, it's just the same equation reversed. Linear distance equals r theta, linear velocity equals r omega, linear acceleration equals r alpha. Good things to know, but that's it. So all of the equations of rotation, they're exactly the same as the rotations for linear. It's just you've got the Greek letters in place of the traditional English letters. So that's how you get those kinematics equations. Now, solving a problem with rotational kinematics, if we look at an example, let's look at a hard drive. Say your hard drive spins up from rest when you turn on your computer to 7,200 RPM in 5.3 seconds, for example. And I want to find the angular acceleration. Okay, no problem. Let's see what we know. To do a kinematics type problem, I'm going to start out by writing my variables. Right, omega naught, it's rotational, so I'm going to do the rotational version. Omega, alpha, theta, and t, those are my variables, and let's see what we know. So I know that it started from rest, so I know that the omega naught, the initial angular velocity, is 0. The final omega at 7,200 RPM. Now, that is RPM. Okay, that is an angular velocity. Now, it's also a quantity that we sometimes call frequency, and we'll talk about that here in just a second. The 5.3 seconds, I know that's time, and I'm looking for alpha, so I'm putting a little question mark by the alpha, and I can see here I've written the things that I know, question mark by the thing I'm looking for. What I don't need is theta. So I don't need theta. I'm going to use my don't need theta equation, which says omega equals omega naught plus alpha times t. That's my don't need theta equation. Now I just need to plug in the stuff. But I run into this little problem here, 7,200 RPM. That's not the standard units. Standard units are going to be radians per second, radians per second, radians per second squared, radians, and seconds. So revolutions per minute, that's not the unit I need. I need to convert that first into the correct unit. So to convert RPM into radians per second, I'm going to rewrite RPM. And anytime you see revolutions per minute, I suggest that you do this. So I'm going to start here with 7,200. Now it's revolutions per minute. I'm going to write it as rev over min. That's what an RPM is. It's revolutions per minute. But it makes it easier when I write it this way to see how to convert it. To get rid of revolutions, it's on top here. I need to put revolutions on the bottom. I want to convert from revolutions to radians. And I know that there are 2 pi radians in 1 revolution. That will cancel revolutions and give me radians on top. I've got minutes on the bottom. Don't want minutes. To get rid of minutes on the bottom, I put minutes on the top. I want to go from minutes to seconds. And now I fill in the numbers top and bottom that make this fraction equal to 1. 1 minute is the same as 60 seconds. So I can take my 7,200 revolutions per minute, I can multiply by 2 pi and divide by 60. So I take 7,200 and I can reduce that to pi over 30 or leave it as 2 pi over 60. So times pi over 30, I get 753.98. So I'm going to call that 754. And that is now radians per second. So I can take this number and say, oh yeah, that is my final omega. 754 radians per second. Now I've got everything in standard units. I'm ready to plug in. So I plug in here and I get 754 equals 0 plus alpha times 5.3. And now you can see I just have to divide by 5.3 seconds, and I get that the angular acceleration is 142 radians per second squared. That's my alpha. Okay? That's how you solve a kinematics problem in rotation.